Right, so this is based on some joint work I did with Mark Holland, Matt Nickel, and Fong Tran. Mark Holland's over at the University of Exeter, and Matthew Nickel and Fong Tran at the University of Houston. So a little bit about myself, I guess. On the spectrum of mathematicians, I consider myself very applied. So I like to ask questions like, how can we use rigorous numerics to inform the direction of extreme value proofs? Or in the opposite direction, how can we use what we've already proven in extreme value theory to create numerical tools and techniques that allow us to better approximate extreme numeric events in real-world data? Right? So a high impact picture. When we're talking about extremes in the IID setting, often we're just interested in looking at the probability of observing some high value, just a single high value. But with the introduction of looking at weak dependence or sequences of weak dependence, we often observe things like clustering of these extremes, and those have some really big impacts in the real world. So for example, this is a picture of Houston in 2017 after Hurricane Harvey, where we had about 4 days of extreme rainfall. And that's not just one street, that's pretty much every street in Houston at that time. In 2019, I'm sure many people remember the series of heat waves that came through Europe. And this is an example of clustering of high temperature days. And then when I moved to Brisbane in 2022, we had 3 days of intense rainfall blamed on some kind of rain bomb along the coast. This is a picture of what it looked like after the water receded outside of my house. And thankfully I wasn't in this, but some people in the audience were. So this is a picture of what Texas looked like in 2019 after a snowstorm blew through. It caused about a week of freezing temperatures, and Texas infrastructure is not really built for something like that. So it caused the turbines to freeze, and it made a lot of people go about 4 days to a week without power. It was really not safe. Also, speaking of turbines, so in an era where we're trying to move from really reliable sources of fuel like natural gas and coal into more variable sources, which are green, like solar and wind, we have to consider these sequences or clusters of extremes in weather. It's actually pretty pertinent to Australia, because Australia's leading the way sort of in green energy. And it's really complicated, but I'll try to draw out what their infrastructure looks like for the grid, the power grid. Okay. That's what their power grid looks like. So hopefully I've motivated a bit about why we can really want to consider clustering and extremes. But before I go into our results, I'd like to just do a dive of extremal clustering and background literature from my perspective. So like all people in extreme value theory, I think we should mention Fisher and Tibet in 1928, who led the charge in looking at extremal distributions for IID sequences. So this is without clustering. And Nadenko, who put all of these together in what we call the generalized extreme value distribution. So we have things like this, where we define our sequence of maxima for x1 through xn being IID, sometimes also in the weakly dependent setting. And we define an extreme value law in this way. So we have to do some normalization on x1, but if we have IID random variables, then Fisher, Tibet, and Nadenko told us that we have some extremal distribution, and that's e to the negative tau. And we can pick our sequence of thresholds un to look something like this. And so in statistics, this looks a lot like normalizing our maxima in some way. So we get out a distribution that's familiar. And this is one of three types of distributions. The first called the Gumbel distribution, the second the Frechet, and the third the Weibull distribution. And thanks to Nadenko, we can put all of these together into a single distribution, which we call the generalized extreme value distribution. And this has three parameters: a location, a scale, and a shape. And the shape tells us the tail behavior. So we have those three types come back out. So if we have a positive shape, we have a bounded or polynomial decaying tail. A negative shape gives us a bounded tail, and a zero shape gives us an exponential tail. Okay, so independence is obviously not a good assumption for anything in the real world. And thanks to Ledbetter in 1974, we no longer have to make this assumption. Ledbetter looked at first creating these two new conditions, which we called the dependence conditions, D and D prime. And this was originally for AR1 processes. So the first one being D is something like a decay of correlations, and D prime is like a recurrence requirement that we'll see later. At the same time, Pickens, who was a statistician, was looking at over-threshold models for extremes, so that will come back later. And then in 1981, Chernak picked up from where Ledbetter left off and looked at ARK processes and introduced another condition called decay, which allows for not just dependence on one time behind, but k times behind. And then finally, Ledbetter generalized these and the general conditions, D and D prime, that we all reference, typically in 1983. Now, like I said, with this introduction of weak dependence, so we end up with something new. And this new thing is like clustering of these extremes. So we can do the same thing we did before in the definition of an extreme value law, where we have some normalization on our x's, but now x1 through xn are only assumed to be stationary. And as long as they satisfy two dependence conditions, I wrote D and dk, but these can be any variation for our context. And if we have a limit that exists here, that limit is now e to the negative theta tau. So theta is this new index that represents the short-term dependence we observe in the system, and it causes this clustering. Now, an argument here is that 1 over theta roughly measures the average cluster size, and maybe we can talk about what theta actually is. Okay. So another statistician, Smith, R.L. Smith, did a lot of work in extreme value theory. So from 85 to 88, Smith looked at things like convergence rates of these maxima, so their limiting distributions, and some statistical fitting methods that we use today, like maximum likelihood estimation. And this will be pertinent in a minute, but Rootson started asking questions like, can we get an extreme value law for these running average values, so ARMA models, but these running averages are take values that are independent and identically distributed. Okay, so with the introduction of the extremal index, we would like to be able to estimate that in some way. And O'Brien in 1987 used Ledbetter's definition, so this limiting distribution e to the negative theta tau, to write out a probabilistic version of what the extremal index would be. And that's typically what's used today in dynamics. Then Singh took a different route and looked at instead the distribution of returns of these extreme values. So under the assumption of a compound Poisson distribution, okay, proposed that the extremal index is the parameter that tells you how large the cluster size is in that distribution. And I think that that was spoken about in the last talk bit. Okay, so again, Smith and Davis, who were two very statistical people, started considering the generalized Pareto, but for weakly dependent sequences. And this is where the statisticians started caring about a definition of the extremal index. And that's because the generalized Pareto needs an extremal index equal to 1. So it was proposed that if you found the extremal index for a nonlinear time series, you can somehow divide it out and then fit a generalized Pareto to the data. So Smith and Weissman looked at things like runs and blocks estimates of extremes. And what they did was just set a really high threshold and then counted the average average cluster size above that threshold. So one fun fact was that the reason why Smith was so interested, or one of the reasons, was because he was looking at returns of Chernobyl-type events using measures of radiation, over threshold measures of radiation. And then finally, Coles sort of culminated all of this stuff that the statisticians did and a bit about what Ledbetter did into a book that we all often reference, which is the statistical modeling of extremes. And he also considered things like weak dependence and non-stationarity in that. And then in 2003, Farrow and Seekers looked at making a better version of an approximation for the extremal index and actually used maximum likelihood estimation on Singh's estimate of the extremal index to be able to give us the numerical estimate that we all often use today. And it wouldn't be a dynamical talk without referencing the two dynamical versions of our dependence conditions, D and D prime, introduced by Freitas, and Todd in 2010. Let's see if there's anything else I'd like to say about that. Oh yeah, so it's not really fair because I've skipped a lot of people between 91 and 2010 that did a lot of work in dynamics and extremes. So maybe we can just call out people like Collet, who before these dynamical versions of D and D prime existed, did a lot of work in dynamics and extremes in that setting. So I know that most of you know this, but I'd like to put this up so I can do a comparison between what we do in dynamics and what we do in real world data. So in a dynamical system, we typically consider our space X some kind of measure preserving map, ergodic in my case, T, some absolutely continuous probability measure. I'm going to abuse notation a bit and use P as my ASIP, but also as the traditional probability that we know and love when it comes to taking the integral over some density. Okay, and then we introduce some observable, which is a function of the distance between X and a point or a set in the space. And then we have a stochastic process which we form, which is that observable taken on iterations of the map. So as the map evolves, the observable changes. And to prove our limiting distribution, we just prove some version of our dependence conditions, so the dynamical versions of these dependence conditions, by choosing UN appropriately, so that we have our normalization requirement on x1, which is just phi of x. And often we consequently derive the extremal index in the process. So this is just a result by Collet. I didn't actually write out what it was or how it was derived, but I just wrote out sort of what the probability is. So probability of some maxima, we choose UN in such a way that we end up with this limiting distribution. And if you look it up, it's just e to negative tau over 2. So that the extremal index is just 1/2 here for the doubling map. All stuff people know. But from the nonlinear time series perspective, we don't know the set of functions that describe our system, right? All we get out are measures of something. So for example, daily rainfall. Now, what we do is we guarantee weak dependence by blocking the time series. And we steal this idea from Ledbetter's argument, who borrowed it, from Gumbel, who borrowed that from Markov. And it's just this idea that we have some really long time series that we break up into pieces. And if we take the maxima over a long enough piece, each of those maxima is roughly independent and is in the limiting distribution that we need. So this is called the block maxima method. And then we use those to create some sort of frequency plot And we use maximum likelihood estimation to get the location and scale out. And that's just implied that UN takes this form that we're all accepting. And we can assume the limiting distribution is the GEV. Now, the problem with this is that when we block the maxima, it forces all interpretable information on the clustering to go away. Because we're taking one value that's really large. We're not taking all of the values that are clustered together. So all we can really say when we fit the data in this way is what's the probability of observing some single, in this case, yearly maximum of daily rainfall above some extreme threshold. Now, there is a nice property of the GEV, and that's max stability. There's some relationship between the GEV we obtain and the extremal index. But the only thing is that we actually only get out this mu star, sigma star xc when we fit the maximum likelihood estimation. So even though there's a relationship between our location and scale and the extremal index, we don't know what that is. It's just one number that comes out. So a natural thing would say, well, okay, we'll use Farrow-Seeger's estimate. We'll get the extremal index in that way. And we can do that. So this is a plot of the extremal index for daily rainfall along eastern Australia. And you see that we can get some understanding of how storm systems move. And that's that they are really big at the north, and they sort of break up as they move inland and they move down. So we can get an average understanding of how things change in our system, but we don't really get this information on consecutive extremes. So that's where things like functionals come into play. So in this case, we consider functionals that preserve things like the consecutive properties. So we can consider things like the k-window time average functional. So if this is really large, then there are some values inside that window that are large. Or the k-windowed minimum functional, which says that if one of those values, if the minimum is above some value, then all of them are above that value in that window. Lucarini did some work looking at the time average functional for dynamical systems, but this required K to be quite large. So in this talk, then, we'll establish some expectations on these limiting distributions for the functionals themselves, and then use that information to pull it back into real-world modeling and try to get better estimates. Okay, great. So I know we've alluded to this a lot this week, but well, in these last 2 days, wow, it does really feel like a week. But I thought I'd just write it out. So we have 3 classical observables that we typically consider in the dynamical framework, and this will be pertinent to us in a bit. We have these negative log of the distance, and that gives us a type 1 distribution. If we choose the distance to some negative alpha for a positive alpha, we get a type 2 or a Frechet distribution. Okay, I just cited your 2012 paper because it was listed there. Do you have a reference for it? Okay, all right. And then the last one is just some constant minus the distance between x and a point or a set in the space for a positive alpha, and that gives us a Weibull distribution. So here is the general lemma from our paper. It says that if we have a Frechet limiting distribution, and xn is some sequence of some weakly dependent sequence, mn is the maximum over x1 through xn, yn is this minimum functional or an average functional. We'll focus on the minimum today. And bn is the max of those. Supposing that the maxima mn have a GEV limiting distribution, bn also have a limiting distribution, we can choose wn to be some function g of kt, so depending on the window size and the dynamical system that we have itself, multiplied by our UNs, which are chosen specifically to give us this normalization on X, then the shape parameters of these two distributions are the same, and we get some relationship between the location and scale here. Yn is either a minimum function. Where? Yn? Yeah, it can be either the minimum functional or the average functional. Right. But we'll focus on the minimum today. Results for the minimum. This isn't really fair because it's an example in the IID case, but it gives us some motivation for our educated choice in AN and BN. And that's just that if we have XN, some sequence of IID standard Frechet random variables, and we choose AN and BN in this way, then we end up with a Frechet limiting distribution. So this just provides the motivation for the AN and BN that we choose in the next slide. So in a similar way, let's let BN be 0, UN to be AN times Y, and WN to be G, so some function of the window size and the map, multiplied by AN times Y. Okay. Oh, okay. Yeah, it went quite quick. Mu2 is the mean for e to the negative theta 2 tau. Well, location. Yeah. Oh, no. Yeah, absolutely. Okay. This is a lemma that tells us max stability. But it will change that. I mean, our choice of Y will change G. Okay. So we make the assumption that we have some limiting Frechet distribution. For some fixed large n, we're in the regime of our generalized or our extreme value distribution. So this is G, and it has an extremal index theta 1. So just write it in that way. And for Bn as well, so we're in the regime of our extremal distribution with extremal index theta 2. And then we can rewrite An as little an over big An times An. So this is just some algebra. And then by this consequence of max stability of the GeV, we end up with equal shape, and then some relationship between mu1 and mu2. So the location of the distribution for Bn and mu1 is the location for the distribution of Mn in a similar way for the variance. Okay. So this is just a consequence of max stability. Good. All right. Writing, so I was going to wait for Okay, great. Okay, so here's an outline of our approach. So, of course, the goal is to find an appropriate G of KT for each system. And to do that, we first have to establish that an extreme value law exists for Yi. Then we have to estimate the extremal index theta 1 and theta 2. And we use some dynamical version of O'Brien's formula. So this was this probabilistic estimate of the extremal index that I mentioned before. And then we have to estimate the scalings UN and WN. In our paper, we do this for some hyperbolic systems. So piecewise C2 expanding maps of unit intervals. You can think of like the doubling map. Hyperbolic twirl automorphism, you can think of things like the cat map. And then weakly coupled systems of expanding maps. So this is like beta maps that are coupled in some way. Okay, so here's our example minimum functional. So if yi is the minimum functional, phi of x, so our observable is maximized to some invariant set, and it has a, we chose the observable so that we have a Frechet distribution in the limit. So in the setting of expanding maps, our lambda here is just the derivative at some fixed point. So the point is our invariant set in that setting. In the setting of a hyperbolic toral automorphism, our lambda is just the expansion in the unstable erection. And then in the case of coupled expanding maps, so these are beta maps, so it's beta x mod 1. So our lambda depends on our coupling parameter gamma and that beta. Okay, and then as I said before, we let our observable be the Frechet observable. And we assume that Mn has a GEV with parameters given by C1, so that's our shape, sigma 1, our scale, and mu 1, our location. Then Bn also has a GEV with the same shape, and then this relationship between the location and scale parameters, where alpha is just the shape. Okay, so just point out here, and we'll see it in a second, that the extremal indices here are the same. And so our G of kt is just lambda to the negative k minus 1 alpha, where k is the window size. Okay, so here's just an outline of the proof. First, we have to set it up, and then we'll do an outline. We're going to consider the observable taken on iterations of a map, our map, so A, B, or C. We're going to choose these sets UN, where our observable is greater than our threshold, and A and Q, where we start really close to the invariant set of singularity, but then we move out for Q iterations. And then we can use this version of O'Brien's formula, which gives us an estimate of the extremal index in that setting. And then I haven't defined them because I put them at the end, but for those of you who are interested in looking at them, but we also have these dependence conditions that we have to show that depend on this definition of UN and A and Q. Okay, so here's the outline. If T is either A, B, or C, so if we can remember those, we have uniform repulsion from some invariant set in the settings. Our observable is our Frechet observable, and we consider our observable taken on iterations of our map, but our invariant set can either be a point in the space or it can be a singularity set. So in the case of, say, coupled expanding maps, if we take a plane of synchrony, so if we take a two-coupled set of expanding maps, then the invariant set's just the line at x1 equals x2. The line in space. And UN is some neighborhood around that. So we're looking at expansion away, or repulsion. Okay, good. So our minimum functional is just given by the minimum of our observable taken on iterations. And we define Wn in such a way that we have this normalization requirement for Y1. But we note that because we have uniform repulsion, Y1, which is just the minimum of our observable taken on iterations, and of the map, and the map is pushing away from our set of singularity. So that value is just lambda to the negative k minus 1 alpha times phi of x. So our set is just some scaled version of phi greater than un. So that means like our time series of yn is just some scaled version of the time series of xn. And in that case, all of the conditions follow, so the extremal index is the same. And the conditions Cyrillic D and Cyrillic D prime Q, which we proved for these kinds of systems in 2021 hold for Y. Okay, and then what this means is that our set choosing Wn so that we have our normalization requirement implies that we also can choose Un to be G of KT Wn, which gives us the normalization requirement for Xn or X1, and then we're done. So I mentioned that I'm really interested in the numerics part of this, which means that I can't help but run numerics on these things. Before I get into this, I'd just like to point out that we do have to use some results that were really paved by David Ferranda, but people like Valerio Lugrini and Gladilo do a lot of work in this area as well. But for those of you who are interested in how we can trust the numerical results we get here, for chaotic systems where we obviously have some error in numerics, chapter 9 of extremes and recurrence is a really nice start for that. So this is an example for the doubling map. Our expectation from our theorem is given in black line, and the estimate from just maximum likelihood estimation for the location and scale are given with blue dots, and the 95% confidence interval is here. This is over different sized k's. So minimum over k equals 1, 2, 3, all the way to 10. This is an example of the numerics for the same theorem, but for weakly coupled system of expanding maps. So in this case, we pick 3x mod 1 and 4 coupled expanding maps. Okay, now I always like to ask the question, can we get some inference out of what we do? So not just saying, okay, our numerical results agree with what's been done in theory, but when we actually try to create a numerical tool that gives us something better than we already have. So in this case, I use the doubling map here, and I created some really long Monte Carlo estimate of what the true return level is for the doubling map. And I used maximum likelihood estimation on 500th of the block maxima for over length 10 to the 3 to estimate these return levels. And then I used our theorem estimates as well. So the blue are our theorem estimates, and then the red's just a standard maximum likelihood estimate that we would use in data science. The reason why these work so well compared to MLE is this max stability that we get out of our theorem. So it says that our shape parameter doesn't change, and the shape parameter is really the bottleneck here. So when we're trying to fit a distribution, the GEV, to our data, the location and scale converge quite quickly, but the shape converges very slow. And when we can automatically, in a large amount of data, so in the original set of data, get an estimate of the shape, we can use that to inform what the shape should be, which is the same, for greater and greater windows. And if you look at here in red, this is the distribution of our time series xn. In blue is the distribution of y for k equals 10. So you see that we're just not sampling a lot in the tail there, which makes sense, right? Because having, say, 10 over threshold values that are really large is the probability is quite low. In fact, we can actually estimate all the way out to k equals 20, this tail decay estimate. So it tells us that the shape is the same, even if we can't fit the MLE. So we were discussing that maybe we could use this information to better approximate these functionals for daily rainfall data. And that is estimate multiple days of high values of rainfall. And the idea was just, well, rainfall might behave like a distance from an invariant set because you have some maximum rainfall in the center of a storm system. And as you move away from it, it gets smaller in some sense. So from this, our theorem, we expect that our location looks like this, right? So we have some lambda parameter, which we actually don't know, but we estimate our lambda as 1 minus theta, and we can do a Farrow-Seegers estimate of theta. Right, yeah. So that's really key there. Rainfall's Frechet. So all of these are for the Frechet. That's right. No, right. It would be sitting over. Exactly. Thank you for that. So we would expect sort of to be within this theorem that we've created in some sense physically. And what I did here was just take the log. Okay, so that way we can look at a GLM, which we call generalized linear model of these location and scale. Our theorem is in red, and then some regression estimate of what the location and scale are in blue, and then we've got some confidence intervals of that regression, which says that, well, they sort of overlap with the theorem themselves. But I think even more compelling is just the result that we get out comparing our estimates from our theorem to the maximum likelihood estimate of this distribution. So our estimate is in blue. It's not perfect, obviously, but the maximum likelihood estimate for the same size blocks are red. And really, this comes down to the max stability we get out for the shape. That's really the key there. Great, so I still have some time. We also have some results for phi maximized in an invariant set, but with a Weibull distribution. And you'll see that this is slightly different. So our observable now is taken to be some constant c minus the distance between x and some point or singularity set in the space. Here we get the same sort of max stability, and that we have the same kind of shape, but the location and scale have a different relationship than in the Frechet case. Now, we know pretty well that temperature follow a Weibull distribution, and that's because Weibull has an upper bound, and thankfully, so does temperature on Earth. So, first, we check that our theorem works for our standard dynamical systems. So this I didn't write here is actually for the doubling map, that Weibull observable. This should not say rainfall, so it should say temperature. This is daily temperature data from Germany. The only thing in this setting is that we don't exactly know if we can assume that this behaves like distance from an invariant set. So instead, we want to just see if we can get some numerical inference out of this max stability property that we observe. Okay, so in this case, it's just to apply the lemma that I stated at the beginning, and then try to estimate what this g of kt is on the data itself using generalized linear models of the variance. And then from that, just making a prediction on what the location would be. And the dots are the real data, and the line is the prediction. There we go, now it says temperature. So this is 10 years. So it's hourly temperature data, but then we're taking blocks of 10 years. It's quite long. So it's different than in the rainfall case where we're looking at yearly returns. And that was simply to make sure that we're in a semi-stationary environment. And it's anything past also 1995, because we know that at least at the bare minimum, there's a jump in 1980 in temperature. So I'm not saying that temperature is stationary, just that we chose this so the variation's quite small. I didn't calculate the 95% confidence interval here, but it would be very similar. So we have our 10-year block size, and I just said from 95 to 2018, these hourly temperature values. And our lemma is in blue, and the maximum likelihood estimate is in red. The Monte Carlo, which is just using all of the data we have available, are the black dots there. And this is for k equals 8 and k equals 10. That's right, in 10 days. Above the return level being the temperature there. Red? So it's fitted to 500 blocks? No, they're 10 years, so they're fitted to, I don't remember, but less blocks. And so, but so is our lemma. No, it assumes a generalized extreme value distribution, and then it fits, it does likelihood estimation on the log likelihood. And it really is the shape that's so bad here, causing the MLE to not work. So we also have results for the average functional in this paper, which I won't go through for both the Frechet and Weibull limiting domain, but there are some issues that we encounter in those cases. I'll just leave it at that. So I'd just like to talk a bit about some further implications in the last few minutes. So I've said it over and over again, but really the results here extend max stability for the minimum and average functionals in the Frechet and Weibull domains, which means that we can do an MLE on the original time series to get some estimate of the shape where we have the most data, and so I have a better fit, and then use that shape to make predictions on what our distribution would look like for greater and greater windows. Windows, yeah. I mean, that's right. In the case of the minimum functional, yeah. Exactly. So what's common actually is I've done a lot of like reviewing for papers in engineering and climate. And what's common, because there are no tools and techniques, is sort of blind fitting of the data. So they want to see a distribution for some average over a window of, say, 1 week. They'll just fit the GEV to that average, get out some shape, which is often negative, so bounded, because there's no data in the tails. So these results actually address a really big need, I think, in the statistical extremes community for people who are applying this stuff. And now I'm currently working on a project which uses the max stability property to estimate returns of multi-day precipitation across eastern Australia. And this is just one image of the paper that we're working on, which just shows that as you increase this window size k, you need this longer and longer block to be able to estimate the shape parameter appropriately. So it gets to the point where it's so long that it has to be the same length of the data itself. Right? And from this information, so we've actually done the fitting already, We observe a very similar trend in the location and scale parameters, and that this decrease because it depends on the extremal index, which is decreasing itself. But you'll notice that even though on the whole the location and scale decrease, the SOI for the scale increases. So what this tells us is that the Southern Oscillation Index plays a bigger and bigger role as we're looking at longer and longer windows of extreme rainfall. Southern Oscillation Index, so it tells us something about ENSO. And then we were also interested spatially how these extremes in rainfall are being affected. So for 3-day consecutive extremes in rainfall, we see that we have a much greater increase in the probability of observing consecutive 3-day high values of rain inland, but not so much along the coast. So the coast doesn't really change much according to the Southern Oscillation Index, but it does change a lot as we go inland. So that's where we get this idea that on average with El Nino, we see less rainfall. Okay, so some ongoing projects that we're working on. So we're going to investigate convergence rates and optimal block lengths for these functionals. So we can give people some estimate based on some work that was done by Smith, but we'll translate that to the functional case of the block length that they should choose a priori. We are going to try to create some statistical fitting methods based on this max stability property, and then we're going to work out some results for the Gumbel domain, which we purposely skipped here. And that's all my talk. Thank you.